Dear students, Namaskar. Welcome to this learning and inspiring series of chemistry of D block elements, quantum chemistry and spectroscopy. Hope you have learned from various lectures in this series. Today I am going to discuss about photochemical and thermal reactions. The content expert of this module is Dr. Rampal Pandey from NIT Uttarakhand and Dr. Sumit Kumar from Magad University, Bodh Gaya. Dear learners, as you are already aware that light is an electromagnetic radiation which has a range from radio wave to gamma rays. Scientifically, we may say it as a flow of photons. These photons have various properties in common to material particles. Photons travel at a speed of light irrespective to the frame of reference. As per Newtonian mechanics, photons do not have a definite mass and so its rest mass is 0. But the important point here is to remember photons have a well-defined linear momentum as well as energy for a particular frequency nu and wavelength lambda of light. The linear momentum p and energy E of photon are hc by lambda and h nu respectively. The intensity of light depends upon the number of photons for a given area and time. That why increasing the intensity of light increases the number of photons incident on a particular surface area within a certain time. When a photon collides with the material particle, it may partially or completely transfer its energy and may or may not be absorbed. Hence, the total momentum and total energy remain conserved, but the number of photons is not conserved during the collision. Many reactions initiated by absorbing the photons in various wavelength regions of spectrums. Let us now discuss about these reactions in detail here, coming to photochemical reactions. Let's define it in a simple way. What is photochemical reaction? Photochemical reaction is a chemical reaction triggered by the absorption of energy in the form of light. You must recall important laws of the photochemistry like Grothus-Draper law, Lambert-Beard law, Stark-Einstein law, photochemical equivalence law, which we have already discussed in our earlier lectures. So, now let's compare thermal and photochemical processes. Effect of temperature can also be seen on photochemical reaction in case of secondary processes irrespective to the primary processes. The primary process depends on the absorption of the light photon and hence theoretically independent on the temperature. Secondary process depends on intermediates such as radical or reactive atoms formed in the primary processes. Generally, the activation energy for the formation of these entities are very small and require a small temperature coefficient, whereas large activation energy requires large temperature coefficient. Want to note here that photochemical reaction having quantum efficiency but no impact of temperature on the reaction processes as reaction depends in a single step. Quantum efficiency is the ratio of number of molecules reacted and number of photons absorbed. The molecules in the ground state absorbs light and undergoes transition between various states of molecules, which is described in the Jablonski diagram. This diagram you have already learned in your previous lectures, but still you can see on your screen. Jablonski diagram I have already discussed with you in module number 34. The diagram shows the vertical arrangement for electronic states as per its quantized energy and horizontal arrangements for the energy states having similar multiplicity. On absorption of light photons, the excitation occurs from ground electronic state S0 to various excited states of Sn. Further, Cassa's rule describes that emission spectrum of excited molecule and it also stipulates that photon emission can occur from the lowest excited state to specific multiplicity. The rule describes that the molecule in higher singlet state relaxed to lower excited state S1 through radiationless delay or internal conversion. Further, relaxation to ground electronic state can occur through either by internal conversion or by an allowed radiative transitions from S1 to ground electronic state. The vertical transition is denoted as fluorescence, which has a lifetime in between 10 to the power minus 10 to 10 to the power minus 9 seconds. Since Cassa's rule demonstrates the photon emission only from the lowest excited state, the emission wavelength is independent from the excitation wavelength. Cassa's rule is further explained by Frank quantum factor. The factor explains the degree of overlap between two vibrational wave functions corresponding to excited and ground electronic states. The transition from higher to lower electronic state will be fast as this overlap becomes significant. It occurs when two vibrational levels come closer to each other, which is in case of vibrationless level of electronic states. Here, the transitions from higher vibrational energy state to lower excitation state S1 and eventually to ground electronic state S0 through fluorescence process. Interestingly, sometimes the excitation state S1 undergoes spin inversion to generate a triplet level having two unpaired electrons. As per Hund's rule of multiplicity, the triplet state T1 is very much stable than singlet state. Thus, the transition from triplet state to ground state occurs through phosphorescence. Due to the violation of spin selection rule, the phosphorescence is much slower than a fluorescence process, and hence phosphorescence has a longer lifetime than fluorescence. Now, let us discuss about the experimental setup for a photochemical process. The schematic diagram for a photochemical process is shown on your screen. Here, S represents source of light emitting adequate intensity in the desired spectroscopic region. L represents lens and M is a monochromator to use a particular wavelength of light. P represents a photochemical cell containing the desired reaction mixture, and R is the receiver for the measurement of the intensity of light. Initially, the cell is filled with the solvent and exposed to the energy originating from light source for a particular interval of time. Further, the cell is filled with the desired reacting mixture and the same process is repeated for the same interval of time. The total energy absorbed by the reacting mixture is calculated by taking the difference between the energy received by the receiver. Quantum efficiency for a reaction help in understanding the nature of secondary processes and the mechanism associated with the photochemical reaction. The molecule is excited to higher level on absorbing energy of resonant wavelengths without any decomposition of molecule. Further, the excited molecule dissociates its energy through various ways. The excited molecule may directly undergo pre-dissociation. The excited molecule may emit radiations corresponding to the energy absorbed of resonant wavelength. The excited molecule may emit the energy through fluorescence or phosphorescence process. This excited molecule may collide with another molecule to partially or fully dissipate the energy to the other molecule, which may cause for the reaction on the energy dissipates as heat. Low quantum yield has been observed when excited molecule dissipate the energy through phosphorescence or fluorescence process. The low yield is also observed on the energy dissipation through conversion of kinetic energy from reactant to other molecule or formation of reactant molecules as one of the products. High quantum yield is observed in case of formation of multiple intermediates in the primary process, and the quantum yield depends upon the chain propagating step. Photochemical reaction is omnipresent and its example is spread in different areas. Let's discuss few examples here. Eyes have the ability to see the world due to the photochemical process of rhodopsin, where retinal converts to its tautomers through a double bond in presence of light. Vitamin D is essential for the healthy bones as well as teeth and maintains the ability to fight against several diseases. It is produced in human body by the exposure of 7-dehydrocholesterol to sunlight. Ozone, being essential for the protection against intense UV light produced by the sun, is formed in the stratosphere after the photochemical dissociation of oxygen. Bioluminescence is the photochemical process used in the emission and production of light in marine vertebrates as well as invertebrates, some fungi, jellyfish, firefly, etc. It is a type of chemiluminescence process where luciferase, the enzyme component and a light emitting pigment involved in the reaction. Artemisinin is an important drug against malaria caused by Plasmodium falciparum, which is produced by the photochemical process. Photoisomerization, electrocyclic reactions, free radical reaction and Norris type 1, Norris type 2 reactions in organic chemistry are example of photochemistry. Xerography and photography are also based on the photochemical processes. Now let's discuss about the photothermal process. In simple terms, we can define it as a photothermal process or reaction is the reaction or process involved or associated with generation of electromagnetic radiation in the form of thermal energy as heat produced by the photoexcitation of compound or material. The schematic diagram of the photothermal processes is shown here on the screen. The molecule is pumped to excited state from ground state by using photons of resonant wavelength. Further, the molecule relaxes to ground state by various ways. It undergoes internal conversion and relaxation from various vibrational energy level to the lower state through non-radiative decay. The probability of relaxation from various routes depends upon the levels involved during transition. Each pathway has a specific lifetime and yield. The radiationless decay process produces thermal energy as electromagnetic radiation. These electromagnetic radiations are called thermal waves. Its propagation through the medium is highly dependent upon the properties from where these waves have generated. These waves are generally between few micrometer and few hundred micrometer, having frequency between few hertz and few kilohertz. Now let's discuss about the applications of photothermal process. Photothermal process is in the treatment of laser hair removal, blood vessel reduction, laser surgery, laser resurfacing, etc. Laser hair removal is primarily based on selective photothermolysis. Here, laser beam targets dark matter melanin. Melanin is a chromophore and is of two types, eumelanin, which gives hair brown or black color, and phenylalanine, which gives hair blonde or red color. Dark color hairs such as black, brown or reddish brown compared to light color such as white have the ability to selectively absorb the photons of laser. It heats up the basal stem cell in the dark color hairs follicles, causing its growth. Laser resurfacing is a medicinal technique to treat wrinkles, sun damage, scratch marks, etc. by using laser beam of appropriate energy. This technique resurfaces the skin using ablative and non-ablative techniques. During ablative techniques, tissues are vaporized and wounds are created, while non-ablative techniques do not create marks on the skin. Further, this technique is combined with the liposuction to tighten and smooth the skin. Photoelectric effect is the phenomenon which can be seen when the light has a small wavelength incident on the metal surface to eject an electron from the metal. These electrons are called photoelectrons. A large number of free electrons have been floating throughout the surface of metal, but these electrons are not free to leave the surfaces and hence require a minimum of energy. This minimum amount of energy is equal to the work function of the metal. When the light of a certain wavelength falls on the surface of metal, the underlying photon collide with the free electrons. If the energy of the photon is greater than the work function, electron may come out from the surface of the metal. Sometimes it is also possible that the energy more than the work function may cause only collision between the molecules. Therefore, only those electrons which are close to the surface and have directions towards the surface after collision may come out after absorbing such a photon having energy greater than the work function. Thus, the maximum kinetic energy of the photoelectrons coming out from the metal surface is Kmax is equal to hc by lambda minus phi, where lambda and phi are the wavelength of light and the work function respectively. It is called Einstein's photoelectric equation. Photoelectric cell or phototube is an application of photoelectric effect and its schematic diagram is shown on your screen. It consists of an electron tube having the photosensitive cathode C and an anode A. The cathode emits electron depends upon incident light in different spectral regions, where anode collects the electrons emitting out from the metal surface. The potential difference between the cathode and anode can be changed with the help of batteries and rheostat. The electrons coming out from the metal surface are collected by the anode and measured as the ammeter. Once the photoelectrons coming out from the cathode and move towards the anode, at some point of time, a number of electrons remain close to the cathode, generating space charge. As this space charge repel the upcoming photoelectrons, the increase in the potential applied to the cathode increases the photocurrent gradually, and a point of time it reaches to its maximum value called saturation current. When the potential of the anode is made negative, the electrons coming out from the cathode will be repelled back. This negative potential has been gradually increases and at certain magnitude called stopping potential. The photocurrent is completely stopped. The stopping potential can be related with the maximum kinetic energy of the electrons coming out from the metal surface. Hence, stopping potential is Hc by E lambda minus phi by E. The saturation current increases by increasing the intensity of light, because the number of electrons escaping from the metal surface increases upon increasing the density of photons interacting with the surface, whereas the stopping potential is generally independent to the intensity of light. Photovoltaic cell is a very common example of photoelectric cell and used efficiency for energy harvesting technology. It converts solar energy into electricity. Various types of photovoltaic cell use different combination of semiconductors. The construction and principle of photovoltaic cell or solar cell is very interesting. Its construction is shown in your screen. It comprises two separate layers of p-type and n-type semiconductors, which combine together to form a p-n junction. An electric field is created across the p-n junction as electron moves from positive p-type and hole move towards negative n-type respectively. The photons coming out from sun are a bundle of energy which when interact with the conducting material, that is the semiconductor material, it jumps the electron to conduction band. These electrons are free to move on the surface of the cell, which is collected by the conducting material present in the black side of the cell. The unnecessary use of conducting material in the front side is avoided to increase the chance of sunlight to come in. As most of the semiconductors are reflective, the loss due to reflection is decreased by using multiple anti-reflecting coating at the front of the cell. The efficiency of solar cell is dependent upon the design and material used for manufacturing. The main concern is that nearly 25% of energy coming out from the sun is not capable of converting into electricity by using silicon semiconductor. It is because the band gap between silicon is 1.14 electron volt and the photons having energy less than the band gap is not helpful to kick out an electron from surface of the cell. Furthermore, in the case of economic production, the material used for manufacturing the conducting surface is not pure enough to give the high efficiency, and eventually the efficiency to the cell limit is not more than 33%. Photovoltaic cells are manufactured from various materials such as silicon, cadmium, telluride, gallium arsenide, etc. Furthermore, the crystalline solar cell of two categories, monocrystalline and polycrystalline, are also used. Monocrystalline solar cell consists of a single crystalline unit, whereas polycrystalline consists of multiple crystalline units. So, dear learners, today we have discussed in detail about what is light, photon and its properties, photochemical reaction and its laws, quantum efficiency of photochemical reactions, Jablonski diagram and Cassa's rule, fluorescence, phosphorescence and Hund's rule of multiplicity, experimental setup of photochemical processes, examples of photochemical reaction, photothermal reactions, photoelectric effects, photoelectric cell and phototube and its construction, solar cell and its construction. So, we learned all these things. Hope you have enjoyed the lecture, and I appreciate and welcome your feedback and queries. Thank you very much for listening me.